Welcome back. In part 3, I'll be discussing the proof of the existence of the infinite volume limit. I'm sorry, my terminology is fluctuating. The infinite volume limit is exactly the same thing as the thermodynamic limit that I mentioned before. Okay, so anyway, this is the statement that we shall prove here. For any inverse temperature beta and any magnetic field, the limit in which we fix beta and h and let the system size L goes to infinity does exist. And also this limit is independent of the choice of the boundary conditions. Okay, so as I stressed before, this quantity, this finite volume quantity does depend on the choice of boundary condition, but in this limit does not. And we can also prove that this f is concave in H and satisfies this symmetry. Okay, so this theorem means that we do have some thermodynamically meaningful quantity, which is well defined from statistical mechanics. Okay, so I will prove this theorem step by step. First of all, we shall assume the existence and the uniqueness, or the independence on the boundary condition, of this limit and prove this concavity and this symmetry. This part is easy, and but anyway, let me do it carefully. So first of all, I start from concavity. So let this boundary condition be free or periodic or plus anything. Okay. And then in part 2, P5, we have seen that if you consider the h derivative of f, you get this expectation value of the magnetization density. Okay, so I think I didn't define this before, but anyway, this is the total spin. So this can be interpreted as total magnetization. And then I divide this by the number of spins. So this is the magnetization density as a function of sigma. Okay, and then I take the expectation value. So okay, so let's go back to part 2. So this is part 2p from page 5, and yeah, this is a relation that I just mentioned. So the derivation is rather standard and easy. So please look at this if you forget about this. So anyway, we have this. But we want to discuss the concavity of f, so we want to consider the second derivative. So we have this. So the second derivative is this. Okay. So again, this is a standard calculation, but let me be careful. So this is the expectation value of m sigma. So here's the definition. Okay, here's the normalization condition. Normalization. This is the partition function. Sum of all spin configuration. This is a function that we want to take average of, and this is a Boltzmann factor. Okay, and now you want to differentiate this with respect to h, and then where are h? Well, here you have h, and here also you have h. Okay, so if you differentiate this, then of course this thing drops down here, and as we saw before, please go back to the definition of h if you forget. But anyway, if you take this derivative, you get the total spin. Okay, actually this so this is, I mean, in this definition of m, I divided by L squared, but so I have to multiply this again to get total spin. So anyway, this is this. Okay. And then if you want to differentiate this thing, then you get minus sign, so you get plus z squared, and here's the derivative of z. Okay, and again, if you look at part 2p5, okay, yes, this thing, we know what this is. So let's go back. So we know that this is this. So this is basically the unnormalized expectation value of m. So we have z here. So what do we get? Well, here what you see is that we have beta L squared. That's out. Let's pull this out. Then here we have m. So this is the expectation value of m squared. Okay. From here, you have expectation value of m, and with this we have expectation value of m. So this we have the expectation value squared. Okay, and now this is very standard, and you know that you can rewrite this in this form. I think you have seen this in statistical mechanics, probability, quantum mechanics, everywhere. Okay, and if you take the square root of this thing, you get the variance. no, standard deviation. Oh, okay, so this, I think this guy is called variance. But anyway, whatever it is called, you can rewrite this in this way. Now here you have m minus expectation value squared. So this quantity is of course non-negative. So this expectation value is of course non-negative, and you take this minus sign here. So this whole thing is non-positive. Okay, so you got this relation. The second derivative is less than or equal to 0. And this means that this f is concave in H. Okay, so I think this is the standard definition of concavity you learned in many classes. But then if you know that this function satisfies this, and then we know that it is concave in a more rigorous or in a more abstract definition. So you can, so this is part 1, page 1, and here's the definition of concavity. And you can show that f, okay, you can show that if G is twice differentiable and if it satisfies this, then this inequality is valid. And then this G is concave in this abstract definition too. Okay, so here we have proved this inequality. This shows that this quantity, this finite volume free energy density is concave in H in this more abstract sense. Okay. Now, if something satisfies this inequality, and if you take limit and the limit exists, and of course the limit also satisfies this inequality. So this shows that in the limit L goes to infinity, this f beta h is also concave. Okay. Be careful. You cannot simply take limit of this relation, because although this for any L is differentiable, this may not be differentiable. Actually, we are going to show that this is non-differentiable at H equals 0 at low temperature. Okay, so you can never consider the twice derivative of this thing to do rigorous discussion. But in this case, we started with finite L, which is finite L free energy, which is differentiable, and we have proved this rigorously. Okay, we have proved this rigorously. From this, we see that this is concave in this more abstract sense in which we use this inequality. Then you can safely take the limit and show that this is also concave. Okay, so that was the logic. Okay. Okay, let me proceed to the symmetry. So now I take the boundary condition to be free or periodic, but not plus boundary condition. So in this case, you can easily show that this our Hamiltonian satisfies this symmetry. Okay. So I didn't define this before, but I used this. So here minus sigma denotes a spin configuration in which all the spins are flipped. Okay. So this shows that if you flip all the spins, then it's the same as it. Okay, if you have a Hamiltonian with this positive, with this magnetic field, and if you consider the value of Hamiltonian, that is the energy for this spin flipped configuration, it is exactly the same as the energy of the original spin configuration with magnetization sign flipped. Okay, this you can easily find from the definition of the Hamiltonian. So let's go back to part 2, page 3. Okay, so these are the definitions of Hamiltonian. Okay, if you simply flip spin, then you get minus sign, minus, minus. But here, if you have both minus, then it cancels. So this part doesn't change. And here, if you put minus, then this sign changes. That's a trick. Okay, but this works only for free and periodic boundary conditions. Why? Well, in the case of plus boundary condition, if you do the same thing, it's the same for here. But here, if you do this, it's okay if your bond is here. But if your bond it connects inside and the boundary side, then here you fix the spin to be +1. So in this case, if you do this transformation minus sigma, and something wrong happens. So this discussion does not work for the plus boundary condition case. Okay, so for free and periodic, anyway, we have this symmetry. Okay, then now we want to show that this partition function has this symmetry. Okay, so why? Well, first of all, this is just the definition. Okay, then here I can write this like this. Did I use this? No, not yet. This is just a trivial rewriting. I'm just summing over all possible sigma. So in this case, it's exactly the same as summing this thing and summing this thing. Okay, is this clear? For example, suppose that you sum from -3 to 3, some any function, any function. But you know, this can be written like f minus f. I don't require any property for f. You can just simply write this like -3 plus -2 plus plus f3, and this thing is also the same. Okay. So this is just a trivial rewriting. Now I use this symmetry here, and this can be written in this way. But if you look at this, and if you recall the definition, this is nothing but this. Okay. So now you simply take the log and divide by minus beta L squared to get this, to get free energy density. And of course, from this, you see that the free energy density also satisfies this. And then you take the limit in which L goes to infinity. Again, we assume the existence of, we are assuming the existence of the limit. And so we get this. Okay. And this is an important note. So as I said, this argument does not work if I use plus boundary condition. And actually, this it simply does not work. But this free energy, finite volume free energy for the plus boundary condition does not have this symmetry. Okay, there is some difference between this and this. Okay, and so this means that the symmetry, in this case, in the case of plus boundary condition case, the symmetry emerges, or symmetry is restored only in the limit where L goes to infinity. Okay, and so this means that if you want to prove this by sticking onto the plus boundary condition, of course that is possible, but that is very tedious. You have to prove the emergence or the restoration of the symmetry. Okay, but if you use free or periodic boundary condition, this comes for free. It's quite easy. But this is not a cheat, of course. We can do this because we know that the limit is independent of the boundary conditions. Of course, we have to prove that, but we are going to prove that next. Okay. Okay, so as I promised, next I'm going to prove the independence on the boundary condition. Again, we assume that this limit exists. So now this is the infinite volume limit for the free boundary condition. So let's assume that this exists. And of course, we are going to prove this later, but for the moment, we assume this. And then we are going to prove for periodic and the plus boundary condition, this limit is exactly equal to this. That is what we are going to prove. Okay, so now I copied from part 2 the definitions of the Hamiltonians. Okay, so we want to compare this. But first of all, as I stressed before, this magnetic field term are exactly the same. They are the same. And these interaction terms are slightly different, but the difference is only in the choice of these bonds, and the difference is only at the boundaries. So let me look at the picture again. So, oh yes, here's the picture. Okay, so for the free boundary condition case, I only use these bonds. And for the plus boundary condition case, we use all these bonds. So these bonds are added. And in the case of periodic boundary condition, we use these bonds. So these bonds, which connect to different sides, are added to this. Okay. So if I consider the difference between the Hamiltonian with the periodic boundary condition and the free boundary condition, the difference comes only from these added bonds. Okay, and the difference depends on sigma. Of course, it may be something. You have to add these things, and it depends on the spin configuration. But in the worst case, if all these terms are plus or if these terms are minus, the worst thing you can get is this. Okay, here this is a set which is obtained by taking away BL from this BL periodic. Okay, this simply means the set of these added bonds. So there are 6 bonds, and this absolute value in my notation, this shows this means the number of elements in this set. Okay, so this is simply the number of bonds which are added to realize periodic boundary conditions. And so in this case, this thing is 1, 2, 3, 4, 5, 6. This number is 6. Okay, and so actually it was L equal 3 case, so you see that this is 2L. This is a worst case estimate. Okay, this difference depends on sigma, but it cannot be worse than this. And the same thing for the difference between plus boundary and free boundary Hamiltonian. Okay, in this case, the difference can be at most this thing. And so in this case, these guys are added. So there are 1, 2, 3, 4, 5, 6. There are 12 bonds. Okay, so in the worst case, we have 12 here. That is for L. Is that clear? So for any sigma, we have this thing, and you notice that these are of course not small thing, and if L is larger and larger, these are very large difference. But recall that these things are sum over all these interactions. So roughly speaking, they are of order L squared. So these quantities are of order L squared, and the difference is of order L. This means that the difference may be large, but relatively it's very small. Okay, so that's the main physical idea for the proof of the independence of the boundary condition. Okay, independence of the limit on the boundary condition. Okay, so let's proceed. So now we are interested in the behavior of free energy. So let's look at this partition function for the periodic or the plus boundary condition. So this is the definition. Now here I want to replace this by the Hamiltonian of the free boundary condition by using the previous estimates. So now I will lower bound this by free Hamiltonian, and then you have to add something else like 4L. Is that correct? Okay. Yes. Okay. Oh, okay. It can be either this or this, but let me take the worst case. So this is the worst case. So the worst case estimate says that this is lower bounded by H3 minus 4L. So you get this upper bound for beta L. Okay. So but anyway, you can bring this here, and then if you look at this is nothing but the definition of the partition function for the free boundary condition. So you get this rigorous inequality. This is upper bounded by this. Well, you can do exactly the same thing. You can upper bound this by, and then you get the lower bound, and you get this. Okay. Now recall that, well, you don't need this, but this is the definition of the free energy density. So you just plug these inequalities into this definition. Okay, then you will find that the free energy, finite volume free energy for these boundary condition is, for example, from this, from here you see that it's upper bounded like this. Why? You take log and divide by this, so you get from here you get this, and from here you get when you take log you get minus 4 beta L, but you divide by this, so you get 4 over L, and same thing for here. Okay, now this is quite nice, and this shows that the difference between this thing and this things is upper bounded by 4 over L. And so if L goes to infinity, this difference becomes smaller and smaller. And so if we assume that this guy converges to some f, and then this becomes small. So this, in the infinity limit, this left hand converges to f beta h, and the right hand side converges to f beta h. And of course, then the limit of this thing must be f beta h. Okay, so this is a proof of the independence of the limit, the infinite volume limit of the free energy on the boundary conditions. And from this proof, it should be clear that you can do much more. I mean, we treated the periodic and the plus boundary conditions, but you can play with any boundary conditions. Okay, the only essence was this. Okay, if you take whatever weird boundary condition you like, but the only thing you have to show that your Hamiltonian with this new boundary condition the Hamilton, the difference in this Hamiltonian with a new boundary condition, and this free energy bound Hamiltonian of the free energy boundary condition is bounded by something times L, which if it is of order L, then all the proof goes through, and you can show that you get the same limit from this new weird boundary conditions. Is that clear? Okay. Now, I want to proceed, just a moment. Now I want to proceed to prove the existence of the infinite volume limit for the free boundary conditions. Okay, then that will conclude our proof. Okay, so this will be, of course, the most essential part. Okay, so now so we shall prove this lemma too, but for this thing, we need this lemma one, which is very important. So what does it say? Well, this lemma says that for any inverse temperature beta, any external magnetic field, then any system size L, the difference between this fine free energy density for system size 2L and the system size L is upper bounded by 1 over L. So this means that if your system size gets larger and larger, this difference becomes smaller and smaller. Okay, this looks very promising for the proof of the existence of the infinite volume limit. Okay, so we shall prove this lemma. This is very essential in the next page. So, okay, let's suppose that this is valid. And we fix beta and h and define Gn for n equal 1 to dot, 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 like this. Okay, so this is simply the free energy density for the free boundary condition for the system size L equals 2 to the n. Okay, so this gives you a series of numbers, and then from this inequality, you get this, because here you set L equals 2n, and then this becomes Gn plus 1, this becomes Gn, and this is this. Okay, and if you're good at this, then you will see that it's done, but let me be careful. So let's take any m and n, and suppose that m is larger than n. Then this difference is upper bounded by using the triangle inequality like this. Why? Well, without absolute value, this is equal to this, right? Okay, if you just sum over this, the biggest term is this Gm plus 1. No. If you plug m minus 1 here, you get Gm, and if you plug this in here, you get Gn. So if you without absolute value, you have this equality here. And then if you take absolute value, the triangle inequality shows that this is upper bounded by this. But now we know that this is upper bounded by this. Okay, and now you replace this upper bound by infinity, and then you can just take sum, and this is upper bounded by 1 over 2, type 2 to the power n minus 1. Okay, and then this relation shows that this sequence is a Cauchy sequence. I hope you remember from your freshman mathematics the definition of Cauchy sequence. It's one of the most essential characterization of the set of real numbers, the completeness of real numbers. This may be the convergence of Cauchy sequence. It's sometimes used as a definition of real number. But anyway, this is a property of the real number, which is very convenient even for physicists, because this ensures that some sequence has a limit, and you don't have to know what the limit is, but this property ensures that you have a limit. Okay, so in this case, we can make use of this. So the fact that this is a Cauchy guarantees that this limit exists. Okay, and so from this, we can prove this very essential lemma. This says that for any beta and for any h, this limit exists. Okay, and so here, instead of just taking L and L goes to infinity, I'm just considering the sequence of systems with system size 2 to the n and taking n to be infinite. Okay, so this is a restrictive form. I mean, this is sort of restricted. You only consider system size 2, 4, 8, 16, 32, dot, 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 dot. But anyway, this looks very nice. I mean, you make the system size larger and larger and larger, and then this limit exists. So okay, so let's define f beta h now. Okay, so we know that this limit exists. So we define f beta h as this limit. Okay. Right. So as you see, this is a very essential statement. And so this lemma was very, very important. So we shall prove this. So by the way, this here we use the fact that Cauchy sequence has a limit. And probably this is the most abstract mathematics used in this mini course. So I think it's a good news. Okay, so anyway, let's prove this lemma 1, which is essential. And again, the idea of the proof is quite physical. Okay, and again, it's based on this order L squared versus order L argument that we have seen before. Okay, so the essential observation is this. So now we consider this lattice, which has size 2L. So 2L by 2L square lattice, lambda 2L. And we shall decompose this into 4 copies of L by L square lattice. So this is a picture. So this is 6 by 6 square lattice. And then we shall decompose this into 4 copies of 3 by 3 square lattices. Okay. And so these guys are identical to lambda 3, but I mean, if I simply like lambda 3, it's quite confusing. So let's add this extra index and call this lambda 3 1, lambda 3 2, and so on. So in general, we have this decomposition. The lattice lambda 2L is decomposed into 4 copies of lambda L. So these guys are all identical to lambda L. And correspondingly, we can decompose the spin configurations because the spin configuration, so we consider spin configuration on this larger lattice. So each spin on lattice side can be either plus or minus. And then, of course, then this gives spin configurations on these smaller parts. Okay, so this is a spin configuration on this part. This is spin configuration on this part, and so on. So this whole spin configuration is written in this form. Okay. Now we can also consider the decomposition of the Hamiltonian. So here we have Hamiltonian for the whole lattice. It consists of a magnetic field term on each spin, every spin, and also it contains the interaction here and here. And again, this is decomposed into the sum of Hamiltonians on these smaller lattices. For example, so I didn't define this carefully, but if this is 1, then this means that Hamiltonian on this lattice. So H1 contains, say, magnetic field on it here. And so if you sum over this, you perfectly recover magnetic field term in here. And also for interaction, you have to be careful. These interactions are also contained in the H1, and these are contained in H2, and so on. But some interactions are missing. Okay, so there are these bonds, which I called cuts. The interaction here and here are present in this Hamiltonian, but not in this sum, because we are just cutting this. And so there are some remaining things. But again, we do the worst case estimate. You just count the number of these missing bonds. 1, 2, 3, 4, 5, 6. 6 times 2, 12. There are 12 bonds that are missing. So that is in general 4L. Okay, so the number of missing bonds are at most 4L. So of course this difference again, so this is a difference between this Hamiltonian on the whole thing and this the sum of Hamiltonians on each smaller lattice. And in this case, of course, this difference again depends on the sigma, but the worst case estimate tells that the difference can be at most 4L or minus 4L, at least minus 4L. Okay. So this is the essential estimate. And I note that the use of free boundary conditions is rather essential. So it can be anything here, but when you consider this decomposed Hamiltonian, it naturally has free boundary conditions. Okay. So this argument can be used repeatedly only when we use free boundary conditions. Okay, anyway, we do have this estimate. So this is basically the essence. And then what we want to do is this. So this is the partition function for the system size 2L. And so this is just the definition. You just sum over all spin configuration on this S2L. and all the spin configuration on this 2L by 2L square lattice, and this is a full Hamiltonian. And now, as for this Hamiltonian part, I will lower bound this by the sum of partial Hamiltonians and this thing, minus 4L. Okay, and you plug this in and you get this. And now here, this is a sum over all spin configurations, but it's the same as sum over these 4 spin configurations on smaller lattices. Okay, and now you can pull this out here, and then you will, now here you have sum, but you can just replace this by product over j equal 1 to 4. Okay, you can rewrite it this way, and then this summation decomposes into smaller parts, and you can rewrite this like this. Okay, if you are puzzled here, please sit down and write down the missing equations carefully, and you will find it. This is true. So now here you have independent sums on sigma j for each smaller lattice of this Boltzmann factor only for this smaller part. Okay, so then this is exactly equal to the partition function on the L by L square lattice, smaller thing. And we have product of 4 things, so we have the power 4 here. So we get this. This is rigorous upper bound. And of course, you can then consider upper bound of this and repeat the same thing, and then you get this lower bound for z. Okay, now you just consider the corresponding free energy. You divide by this. Look, so this is system side 2L, so L 2L squared becomes like this, okay, and log C. And you plug in these upper bound and lower bounds to get this and get this, okay? Because if you take log, I think this is obtained from this. Okay, if you take log, you get 4 beta L, and you have power 4, so you get 4 here and log DL. Okay, and well, it looks like we got extra 4, but no, this is well done. This is in good shape, and this 4 cancels out, and you exactly get this. Okay, and from here you get L divided by L squared, so you get 1 over L. Exactly the same thing for upper bound here, and you get this. Okay, so this proves the desired lemma. Is that clear? So we have seen that the difference between this and this is upper bounded by 1 over L. So this is the, yes, this is a lemma 1, and we have proved it. Okay. All right, so as I said, I mean, this lemma 2 was essential, and the lemma 1 that led to this lemma 2. So lemma 2 was basically essential, and if you don't care about this 2, 8, 16 sequence, then this is almost the answer. Okay, and so this was the essential. But anyway, we want to complete the proof, and we want to show that we can really replace this by general L. So that will be the final step of the proof. Okay, but the argument is basically the same, and it's a bit tricky. So I want to be quick here. And if you want to really digest the details, please pause the video and make further calculations. But I think the idea will again be physical, and it should be clear. Okay, and so we shall use lemma 2 and show that this exists. Okay, and now here this is a bit technical, but we consider the lattice whose size is 2 to the n times L. So we consider 2 to the n times 2 to the n L square lattice, and we decompose it in 2 different ways. Okay, and in the first decomposition, we decompose it into identical copies of lambda L. In the second decomposition, we decompose this into identical copies of lambda 2 to the n. Okay, so here's the simplest case. So here I set L equals 3 and n equal 2. So this is 2 to the 2 times 3. So this is 12. So we have 12 by 12 square lattice here, and we want to decompose this in 2 ways. I'm sorry for this picture, it's not easy to see. But here I'm decomposing this lambda 12 into identical copies of lambda 3. Okay, lambda 3. So there are, I think, 16 copies of lambda 3 here. And here in the second decomposition, we are decomposing lambda 12 into identical copies of lambda 4, 4 by 4 square lattice. And I think there are 9 copies, 9 copies. Okay. Now, corresponding to, again, we decompose the spin configuration and we consider corresponding decomposition of the Hamiltonian. So I'm being a bit sloppy or sketchy here, but you can do the same decomposition as before. Okay, so in this first, we can decompose this into Hamiltonians on these small lattices, and in this second case, we again decompose this into these things. And then again, we do this worst case estimate for any spin configuration sigma. So this is for the first decomposition. The difference between this large Hamiltonian for the largest lattice and this decomposition thing is this. Oh, please believe me, or please check this carefully. Probably I'm wrong, so then let me know. Okay. And then for the second decomposition, you get this. Okay. Then from this, you can prove the inequality for the partition functions, and then taking the log and doing things like that, you can show that this upper bound for the difference in the free energy for the biggest lattice and these decomposed things. Okay, and again, believe me, you will get this. Oh, this looks nice and symmetric, so probably this is okay. Why did I do this? Because I wanted to estimate the difference between the free energy of L by L square lattice and the free energy of 2n 2 to the n times 2 to the n square lattice. Okay, and in order to see this, you have this intermediate quantity. Okay, you can of course bound this by using the triangle inequality as a sum of this and this, right? And then this shows that this is upper bounded by this plus this, which is this. Now the goal is here. Now in this inequality, you can take the limit in which n goes to infinity. Okay, and then this vanishes, this goes to 0, and by definition, we define the limit as f beta h. So by definition, this converges to f beta h. So we have this inequality for any L. What does it mean? Well, this shows that the difference between this guy and this guy gets smaller and smaller as L gets large. So this finally proves the existence of this limit. Okay, so we have here we have shown that this limit exists and it is equal to f beta h, which was defined here in this lemma. Okay, so that is the end of the proof of this theorem 3. Okay, oh here I didn't say I didn't repeat this, but this is theorem called theorem 3 because we proved it in this part 3. Okay, and as I emphasized, this was a bit technical, but this theorem ensures that we have f beta h, well-defined quantity, which represents a thermodynamic property of this Ising model. And this independence on the boundary condition is very important. Okay? And of course, the existence, concavity, symmetry, everything is important. And so anyway, we can rely on this quantity, and we shall sit down and study this quantity. That's what we are going to do in parts 4 and 5. Okay, so that's all for part 3. Thank you for watching.